So the next speaker is Seungjae Lee. He's going to talk about different ways to grow supermassive black hole.
Hello everyone, my name is Seungjae Lee and I'm from Seoul National University, South Korea, and I'm working with Yoon Kim. So today, as you can see in my title, I'm going to present about the modeling tidal disruption accretion of the massive black hole in a galaxy simulation. Okay. Let's start with a very general introduction of massive black hole. I think all of you already know about massive black hole, but the massive black holes are black holes with mass ranges of a million solar mass, and they are found to commonly exist at the most galaxy centers. And they are also correlated with their own host galaxies. And there are many interesting questions related to the massive black hole. For example, what is their role in the galaxy, and what is their formation and evolution history? And more interestingly, the massive black holes are found to exist already at high redshift. There are growing evidence of massive black holes at early universe. Before JWST, we found people observed more than hundreds of samples with mass range between 10 to 7 or 10 to 9, between redshift 6 to 8. And now after JWST, we're finding more and more even more higher redshift massive black holes. Like recently, we found GNZ11 is at redshift 10.6 with million solar mass. But there is one subtle problem that the mass of the massive black hole is very difficult to be explained, because the massive black holes, the growth rate of massive black holes are capped by the so-called Eddington limit. And the Eddington limit is the radiation pressure from the accretion disk blocks the further inflow of the gas. Therefore, it forms a kind of upper limit of the growth rate. So given the Eddington limit, we need a black hole at extremely high redshift, or we need a super Eddington growth, but it is very hard to fully explain in current picture. So we need to advance and devise a new massive black hole evolution picture to explain the observational constraint. So currently we have two types of solution. One is to increase the initial seed mass of black hole. And there are three preferred scenarios. One is the direct collapse of chemically pristine primordial gas, and the second one is the runaway collision in an ultra-dense star cluster. And also, at the early universe, the top three stars remnants may form an initial heavy mass field. And also, we may devise some creative mechanism, like how to, somehow reaching the super Eddington accretion of gas. Or we may find a non-gaseous mass source that is not affected by the radiation pressure. So in my work, I suggest the tidal disruption accretion as a new black hole growth channel. So when a star closely approaches to a massive black hole within a tidal radius, then the star is tidally disrupted by the gravitational force of the massive black hole, and then the bounded portion of the debris forms an accretion disk and accrete onto the massive black holes. So if a massive black hole, and since the star is less likely to be affected by the radiation radiation feedback from the massive black hole. So it may provide the mass above the Eddington limit to the massive black hole. And it may occur frequently in a ultra-dense star cluster like nuclear star cluster. So in my study, I devised a tidal disruption accretion model in a galaxy simulation to test my scenario. But there was one big problem is that tidal radius is actually very spatially small compared to the galaxy scale. As you can see in this navy equation, the length scale is like 10 to minus 6 parsec, which cannot be computationally resolved in the galaxy simulation. Therefore, I had to find another approach to estimate the rate of tidal disruption accretion. So instead of like directly modeling the tidal disruption accretion, I chose to model the tidal disruption accretion in a statistical approach. And the statistical approach is called the loss cone theory. And the loss cone is like, imagine a star has a small angular momentum, then the star will be bound, then the star will pass really close to the black hole in the tidal radius, so it can be tidally disrupted by the black hole. And the set of directional momentum looks like a conic region like this. If it goes like this, then it will not go through the tidal radius, but if it goes through like this, then it will be captured by the black hole. So this conic region is called the loss cone. So if we know the stellar distribution around the black hole, then we can theoretically estimate the frequency of tidal disruption events. But also there is another difficulty. So, no. The star cluster is still small compared to the galactic scale. In a typical nuclear star has like millions or 10 millions of stars in a 3 parsec or 5 parsec size. So it's the distance between stars is too small. So it is still difficult to resolve the detailed profile of the stellar density. So I had to make an assumption of the radial stellar distribution around the black hole. And in my work, I simply assume that the stellar density profile around the massive black hole follows the power law. The motivation is one of the motivations is that in the observation, the nuclear star cluster around the black hole follows a power law like this. In this case, this is a broken power law of the Milky Way nuclear star cluster, and the outer so we can simply assume that the nuclear star cluster follows a power law like this. And there is one another motivation. So given a star given an IMBH, the massive black hole seed formed in a dense star cluster, then it should be formed after the runaway collision in a collapsing core. And the profile of collapsing core follows like almost isothermal core, like following an inverse square law. So maybe we can, for simplicity, we can assume that a radial stellar profile around the black hole follows the power law. I introduced two motivation of my power law assumption. So with this power law assumption, and you can compute the rate of tidal disruption accretion quite simply. If we assume a single power law, then the tidal with slope index -2, then the tidal disruption rate can be given like this. And as you can see in this equation, the rate increases with increasing velocity dispersion of stellar system, and it decreases with the mass of massive black holes. So this dashed line shows the rate. This dashed line, green dashed line, shows depicts the evolution of depicts the tidal disruption rate to the mass of black hole with velocity dispersion 34 kilometer per second. As you can see, as the black hole mass decreases, the rate of tidal disruption increases. But no, if you, as you can see in this plot, it increases like infinitely. So this rather a subtle problem whether that the power loss can be extrapolated in the innermost structure of the nuclear star cluster. So it may produce an overestimation of the tidal disruption rate. So to avoid this overestimation, I introduced a core size, RC. And if we assume a core size then and do some simplification for the modeling, then we can. I made the tidal disruption rate modeling like this, following this. So when the mass of black hole is small, then it decreases with the mass. The rate increases with increasing black hole mass, and at certain critical mass, it again begins to drop. And in my model, it's still on the size of core or index slope is difficult to be resolved, so I just set it as a user parameter that the user fixes, and the density and the velocity dispersion of the stellar system is derived from the simulation. So in my simulation, I just I inserted a nuclear star cluster in a background galaxy, and then at the center I inserted a massive black hole seed with 10 to 4 solar mass. So this is the accretion history of gas accretion and tidal disruption accretion. As you can see, that the gas accretion, which is black dash blue dashed line, does not go beyond the Eddington limit, but it still dominates most of the epoch. But depending on the choice of parameter, the tidal disruption rate, the red wheel line, can grow as much as or go beyond the gas accretion rate. And the effect on to the massive black hole growth was significant. Even the black real line with gas accretion only, then the black hole grows from 10 to 4 to 10 to 5, but it's much below than the Eddington rate growth. But if we include the tidal disruption accretion, then even in the minimal case, it could grow above the Eddington limit. And also, because of the enhanced growth of massive black hole, you could see the total gas consumption rate has been significantly increased as well. To summarize, I want to say that there are still caveats of my work. The one is the innermost stellar density profile is rather uncertain. If the mass of black hole is small, then it may be quite sensitive to the innermost stellar density profile, but it is hard to be resolved. And the accretion efficiency per tidal disruption event is also uncertain. And the evolution of stellar system, which is not still resolved in a high galaxy scale simulation, may affect the entire history of tidal disruption accretion. So I'll end my presentation by showing this summary. So a dense star cluster may be a birthplace of massive black hole, but it can be also a possible mass supply of the massive black hole. And the contribution of tidal disruption accretion is likely to be great, especially at the early stage of massive black hole. As you remember that the tidal disruption accretion rate increases, and then at certain critical mass, it drops. And also, therefore, we suggest that tidal disruption accretion must be taken into consideration in the massive black hole evolution picture. Thank you for listening.
One or two quick questions.
Yeah, thanks for a great talk. I'm Haowen Zhang, and so my question is, do you assume that the black hole is always at the center of the galaxy? Do you allow it to move around in the galaxy center?
Well, in the simulation, the black hole can move, but as I mentioned, the detailed, the close encounter between particles is hard to be resolved because it requires a extremely high resolution. So I just assume that the black hole is, in the model, the tidal disruption accretion model, I simply assume that it is at the center of massive black hole.
Okay, thanks.
We heard about the discovery of these very dense so-called red dot galaxies. Do you think they would be environments where your tidal disruption calculations would be relevant? Have you thought about that?
I'm a little bit cautious about that, but I think it can be a candidate.
How would a reasonable central density in those objects compare to what you've assumed?
Let's chat after this session.
Okay, so the next speaker is still trying to figure this out, so why don't we have one more?
Hi, I'm Zozo. I'm interested in what anisotropy velocity anisotropy profile are you assumed? Would that be another uncertainty for the results?
Yeah, so actually I heard that the anisotropy of the velocity may affect the event rate, but for simplicity, I assume the isotropic distribution. But it may increase if we include the anisotropy effect.
Okay, let's thank the speaker